Okay, so in this video we want to look at implicit and logarithmic differentiation. The main idea is that if we differentiate with respect to y, then we differentiate normally, but just tack on a dy dx at the end. So let's have a look at the first example. So what we'll do is differentiate x cubed normally, we'll get 3x squared. We'll differentiate 2y squared as usual, we'll get 4y. But since we differentiated with respect to y, we'll tack on dy dx. And on the right hand side we'll have 4 and the derivative of y is 1, but with a dy dx on the end. And then we simply collect all the dy dx terms onto one side. I'll end up with a 4y minus 4. If I take this over to here, take this 3x squared over to the other side, I get minus 3x squared. And so what we see is that dy on dx is minus 3x squared divided by 4y minus 4. Obviously for y not equal to 1. Okay, let's look at a slightly more complicated example. Differentiate sine x cos y is 4 times the square root of y. So we differentiate as per usual. Sine goes to cos x. We're using the product rule, so we have cos y plus sine x, and then the derivative of cos y is minus sine dy dx, and we'll differentiate the square root of y. That'll get us y to the minus 1/2 dy dx. Simplifying this a little bit, we'll get cos x cos y minus sine x sine y. Dy on dx is 2 over the square root of y times dy dx. And as before, we simply collect the dy dx terms onto one side. So I'll have minus sine x sine y. Then I'll have a minus 2 on square root of y. And put all the non-dy dx terms onto the right hand side. I'll get minus cos x cos y. So I can put everything, I can divide by -1 and then divide all these terms. So I end up with dy on dx is cos x cos y divided by sine x sine y plus 2 on root y. I can multiply everything by root y, but that's no big deal, so I'll just leave it here. Okay, so let's look at a logarithmic differentiation example. So set this equal to y, and we want to differentiate this. Now to do this, what we'll do is take the logarithm of both sides. So I get log e y is log e x to the x, and by log laws, this tells me that log e y is x times log e x. Now I can differentiate log e y by implicit differentiation. I just get 1 over y times dy dx, and then I just use the product rule on the right hand side. I'll get log e x plus x over x. So what I find is that dy on dx is y times log e x plus 1, and this, we know that y is x to the x, so we conclude that dy on dx is just x to the x and then log ex plus 1. So it's a very powerful technique for differentiating quite complicated functions. For our last example, let's look at differentiating y equals x times log 3y. So to differentiate logarithms that do not have base e, we need to change the base. So what I'm going to do is just call it something else. I'm going to set k to be log 3y. Now if I simplify this, I get 3 to the k is equal to y. And then I'll take log e of both sides. So I log e 3 to the k is log e y. And log laws tell me that k is, well, let's maybe not jump so many steps. So I get k log e3 is log ey. And so I can write log 3y, which we called k, as 1 over log e3 times log ey. So in particular, dy on dx, well, let's do the derivative with respect to x log 3y is 1 over log e3, which is just a constant, times 1 over y dy dx. So in particular, now we can just apply normal implicit differentiation. So I differentiate the left-hand side, I get dy dx. The product rule now tells me I get log 3y plus x times this here. So let's write that. I get 1 over log e3 times 1 over y dy dx. And now I just collect the dy dx terms. Is there a nice way of doing this? Not really. So what I'll do is I'll have 1 minus 1 over log e3 times y. There's an x coming from here, so maybe I'll write that a little nicer as an x, and that is log 3y. Okay, now we just divide by this term and I get dy on dx is log 3y divided by 1 minus x over log e3y. And that's all. So let's just briefly recap the main ideas from the ideas of implicit and logarithmic differentiation. We differentiate when we differentiate implicitly, we do everything in the usual way, but if we differentiate a y term, we just put a dy dx at the end of it. If we want to differentiate something like x to the x, taking the logarithm of both sides can be very useful, and then using our implicit differentiation. This is the idea of logarithmic differentiation. And if we have a logarithm that does not have base e, we need to convert to base e before doing any differentiation. If you like this video, please hit the like button, and if you want to see more of this content, please consider subscribing. Thanks, guys.